Okay, so we have air. We're going to treat it as an ideal gas. And it's an isentropic process. Um, and let's see, from the TDS equations, we have that um, delta S. Well, let me go from so we have TDS is equal to du plus PdV. Um, and for an ideal gas, we know that um, let's see, du is equal to CV, d temperature. And we know that um, P is equal to RT over V. And so we can combine these and we get TDS is equal to CV dt plus RT dV over V. And so ds is equal to CV dt over t. You don't have to do any of this if you have the equation sitting in front of you. Um, plus R dV over V. And so delta little s is equal to CV natural log of T2 over T1 plus R natural log of V2 over V1. And now it's isentropic. So we have that CV natural log of T2 over T1 is equal to R natural log. I flipped the sign, so I'm flipping the V's, V1 over V2. Okay, so that's one of them. And then the other one, I guess, is CP natural log of T2 over T1 is equal to R natural log of P2 over P1. Okay, so these are the two things. Actually, those are the things you can start with. And we have an initial temperature, and we have a ratio of pressures. Right, right. So we're going to use this one, given that P2 over P1 is equal to 0.9. And T1 is 340 Kelvin. And CV and CP, we know because this is air. R, we know. All right, so we're trying to calculate that final temperature. We can do this as, so I'm going to write this as natural log of T2 over T1 is equal to R over CP times natural log of P2 over P1. And then e to both sides gives us that T2 over T1 is equal to e to the power of r over Cp, natural log of 0.9. R for air is 287 in SI units. Cp, so CV is 1005. Cp is 1005 minus 287. Oh no. Oh, there we go. So that is, I can't touch it. Come back. 718. Okay, so T2 over 340 is equal to E to the power of 718 times the natural log of 0.9. And so T2 is
What's the quotient is so 718 is the quotient of R over CP?
no, I didn't do that. That is CP. And so R over CP is, so 287 divided by 718 is 0.4. So this is 0.4. And so I think we get that T2 is 326 Kelvin. And you would just start with those two boxed equations. Okay, and now we have to calculate the work per kilogram. It's isentropic, which means there's no heat transfer. So we have that the change in internal energy is equal to Q minus W. This goes away. We can calculate that change in internal energy as the mass times the change in specific internal energy. We're given the mass, hopefully. Oh no, we're calculating the work per kilogram. So so we'll come up with this in a second. Or we can write it as the change in specific internal energy is equal to negative W divided by mass. Okay, so we have to calculate that change in internal energy. This is a pretty small temperature change, so I'm going to write this as CV times the change in temperature. So that's 1005 for air times 326 minus 340. So you get negative 14,070. Um, and so the work per mass is 14,070.
And that would be joules per kilogram.
Joules per kilogram, yeah. Um, so let's see if this makes sense with what we expect. Um,
Could we possibly use the properties from the website to look up the specific thermal energy and then take the difference between the two?
yes, if they have one for air, I don't remember if they do.
Dry air was on the website.
I don't remember.
Same answer, right? It's like per units, kilojoules or something.
Oh yeah, everything would be the same. Yeah. Um, okay, work per kilogram. Well, this thing is compressed. Um, so we expect work to be negative. We got a positive work. So what's going on there? Um, isentropically. So how would this happen that the temperature would go down if there's no heat transfer? I think the answer is that this thing isn't compressed. Um, it expands. So you could look that up with
Pressure is less than the original pressure.
yeah. So I mean we could calculate that with the ideal gas law. Um, so at state one, uh, we have P times V1 uh, is equal to 287 times 340. And so V1 is equal to 97,580 divided by P, whatever this P is. It's a positive number. And then at state two, we have that 0.9 P times V2 is equal to 287 times 326. And so V2 is equal to 103,958 over P. So it isn't compressed. It expands. Any questions about that problem? Okay. Um, so going back to what I introduced last time. Uh, so last time I gave uh, the second law for control volumes. And that says that the time derivative of the extensive entropy is equal to the sum of all the rates of heat transfer divided by the temperature around the boundary, plus the rate of mass flow in the inlet times the specific entropy at the inlet, minus the rate of mass flow rate at the exit times the specific entropy at the exit, plus the rate of entropy production. Okay, so this is for an actual cycle, not an ideal cycle. Whenever you see one of these uh, squiggly d q's over t's, those integrals, or this sum, you have to ask yourself, am I thinking of an actual process or an ideal process? Okay. And then this thing is the rate of entropy production. And this thing has to be greater than or equal to 0. If it's equal to 0, that means that this process is internally reversible. If it's greater than 0, it means it's kind of everything that actually exists. If it's less than 0, it means that process is impossible. Okay? So sigma dot less than 0 uh, violates the second law. Okay, like we're used to with these control volume problems, most of the time you're going to see steady state. Um, so here's what steady state tells you. Um, the first two of these, I'm going to give you three of them, and the first two are things that you already know. So you know that if something's steady state, any properties inside that control volume stay constant. So d big S dt inside the control volume is 0. Extensive entropy is a property, so there's no change in time if it's steady state. The second one has to do with the masses, the mass flow rates. So m dot at the inlet is equal to m dot at the exit, and we'll just call it m dot. And then the third one, this is kind of two things, but they're related. So if there's no fluctuations in time of properties, then you can go back and forth between, so if a question asks you sigma dot over m dot, or it asks you for sigma over m, those are exactly the same values. Okay. And the same is true with q dot over m dot. Q dot over m dot is equal to q over m. So whichever form like you're asked for, or whichever form is relevant in your problem, if it's easier to calculate the other one, you can do it, and just those are exchangeable. Okay. So these are the three things. And let me just do an example or two. The first one says we have a turbine in steady state Um, Steam enters. This is steam, so we know we're talking about water. Um, and it enters at a pressure of 30 bar and a temperature of 400 degrees Celsius. Um, and a speed coming in of 160 meters per second. And then saturated steam or a saturated vapor, saturated water vapor, exits at a pressure of 1.01 bar. Um, well, we're given the temperature. We really don't have to be. Since this is a saturated vapor, we know that we can look up any properties we want. Um, so the temperature, anyways, is 100 degrees Celsius and a velocity of 100 meters per second. And if we're given, so if the rate of heat transfer per mass that goes through this device is negative 22.6 times 10 to the third joules per kilogram. What's the rate of entropy production per mass that moves through that device? Okay, so this is a turbine. It starts with a really high pressure. It leaves the turbine at atmospheric pressure. So the pressure goes down and that's turned into work. Um, and this heat transfer, this rate of heat transfer is negative. So is that heat being lost to the surroundings or energy moving from the surroundings into the turbine? That's right, from the system onto the surroundings. So that's heat loss, you know. Um, okay, so we're going to go, I'm going to just start out. It's really kind of the same approach that you use for the first law for control volumes. Set up the full equation, make the cancellations you can because of the assumptions, and then we'll start looking for what we can fill in. Okay, so ds dt for the control volume is equal to the sum of all the Q dots over temperatures around the boundary plus mi dot times the specific entropy at the inlet minus me dot times the specific entropy at the exit plus sigma dot, the rate of entropy production. And since this is steady state, this goes away. And I can write this as, so 0 is equal to, there's only one thing that we have to worry about here. So the rate of heat over the temperature plus, and I'll just write this as m dot times the quantity Si minus Se plus sigma dot. And we're given that uh, Q over M is equal to this thing.
Professor,
Yeah.
what is the difference between the sum Q dot over T, like big B, and what it'll be?
No difference. I don't know. I guess I wrote it with a little b before. Yeah, it doesn't mean anything. That B just stands for boundary, around the boundary. Okay, so we know Q over M is just like a synonym for Q dot over M dot. And we know that that is equal to negative 22.6 times 10 to the third. Yeah, so this was just the third one of those things when we're in steady state. What does steady state mean? It means Q dot over M dot and Q over M are the same thing. So whatever form is more helpful to us, that's how we can write it. Okay. And same with Q and same with sigma. Um, so now I'm going to divide everything by M dot. We're trying to find a sigma over M, right? So it kind of makes sense that we would, I mean, it'd be nice to get rid of this M dot here, be nice to get an M dot over here, over here. So I'm going to divide. So we have 0 is equal to, I can write this as dividing this first term by M dot. I can write this as Q dot over M dot divided by the temperature plus S at the inlet minus S at the exit plus sigma dot over M dot. Um, okay, so we have, so 0 is equal to negative 22.6 times 10 to the third. Oh, I see. I just forgot to give something that we need here. The outer boundary temperature is 350 Kelvin. Okay, so this is our Q dot over M dot, the boundary temperature. So remember, the temperature for that heat transfer isn't at the inlet or the exit, it's at the boundary of the device. So this is where we use this 350. And then plus SI minus SE plus sigma dot over M dot. Now we can use the properties we know at the inlet and the exit to calculate that specific entropy. We pretended that I had given that to you at the start. I I just forgot to write it down, but it's given as part of the problem. That's why I was like slowing down, like, wait, where are we going to get that T from? But it was given. I didn't give it to you. Okay, so now we can go to the website for water. And at the inlet, S is equal to 6.92 times 10 to the third joules per kilogram Kelvin. And at the exit, Okay, so this is a saturated vapor. So at the website, how would you look this up? I mean, I guess you could look it up by giving the pressure and temperature I gave you. But if I hadn't given you the temperature, what would you enter to look this up on that website? 7.35 times 10 to the third. So the first property you would give is that pressure, 1.01 times 10 to the fifth pascals. And then the second thing you would have to give is the quality because it's at saturation. So what's the quality of this saturated vapor? One, yeah, exactly. And so now we can say 0 is equal to negative 22.6 times 10 to the third divided by 350 plus 6.92 times 10 to the third minus 7.35 times 10 to the third plus sigma dot over m dot. And you get that sigma dot over m dot, which is the same thing as sigma over m, the entropy production per mass flow rate through this device is equal to 498 joules per kilogram Kelvin. Okay, so this is this is a number that you could try to reduce by making it more efficient. And also this says that this process is physically possible because this is greater than or equal to 0. So what if that was part A and part B now asked, what's the work done by this turbine per mass flow? Well, now we could go to the first law. So dE dt for the control volume is equal to Q dot minus W dot plus MI dot times the quantity HI plus VI squared over 2 plus GZI minus ME dot times the quantity HE plus VE squared over 2 plus GZE. This goes away because it's steady state. And so we have 0 is equal to Q dot minus W dot plus, well, we could punch all this stuff in. Let's say that those cancel. We do have speeds, so we might as well use them, but that's going to be a tiny contribution. And so this is m dot times the quantity HI plus VI squared over 2 minus m dot times the quantity HE plus VE squared over 2. And now you could divide everything by m dot. You get 0 is equal to Q dot over m dot minus W dot over M dot plus HI plus VI squared over 2 minus HE minus VE squared over 2. And you're given this value. So that's negative 22.6 times 10 to the third. Minus W dot over M dot. And then we could look up these values. Let's see. What do we know at the inlet? So at the inlet, we have 30 bar, 400 Celsius. This is water. So 30 bar is 3,000 kilopascals. Temperature is, what was it, 400? So specific enthalpy is 3232 times 10 to the third. And then the second one was at 101 kilopascals and a quality of 1. So the enthalpy is 2675 times 10 to the third. No, it'll be the same.
It's 99.88.
So 2676. Yeah, so there's a tiny little difference there, but and what did we have for speeds? 160 and 100. So this is 3232 times 10 to the third minus 2675 times 10 to the third plus 160 squared over 2 minus 100 squared over 2. And so W dot over M dot, which is the same thing as the work done per mass, is equal to 564,800, and that is joules per kilogram. So that's how much power you're getting out of this, generating from this power cycle per kilogram of mass that flows through the turbine. Any questions about that? Okay, let's do the quiz.